In 1953, a storm surge covered 160,000 acres of land near the mouth of the River Thames in London, killing more than 300 people. If it had reached the low-lying, densely populated areas of London where we're standing now, it would have been even more horrific. The government reacted by agreeing to build the Thames Barrier, essentially a gate across the river, which can be raised when needed to protect both against storm surges coming in from the sea, but also floodwater coming down the river. It was built in 1982, and in its first decade of existence, it was lifted 10 times. In the last decade, it's been lifted more than 80 times. And the kinds of extreme weather events that have seen it be lifted so many more times than was originally forecast are exactly the kind of extreme weather events that are predicted to become more numerous and more intense as a result of climate change. Now, as a consequence, people have started to ask the question, for how long will this 1.5 billion piece of infrastructure remain fit for purpose? Now, climate models can help give us some of the answer, but there's many, their results vary, and there's uncertainties around those results. The innovation I want to talk about today will allow us to collect data about the climate at 10 times the accuracy that we're currently able to, constraining those uncertainties in the models and helping us to determine which climate models to base our investment decisions on much more quickly than we're currently able to. But back to the problem. This chart is from the Intergovernmental Panel on Climate Change, and it shows two different scenarios for what the future temperature rise will be by the end of the century, given two different input emissions. The blue line at the bottom is the likely temperature rise if we immediately start to reduce emissions and carry on doing so quite sharply. The red line at the top is if we carry on emitting as now. And the fuzzy bands around both of these two are the uncertainties, so the different answers to the question, what would happen with this level of input emissions? As you can see, the uncertainties are unpredictably and unacceptably large. Just to take the red band, for example, what that's saying is, if we carry on emitting at our current rate, the answer to the question, what will the temperature be by the end of the century, is it will be somewhere between 3 degrees more than now and 5.5 degrees more than now, which corresponds to a massive range in the potential impacts that we would see, and a huge range in the amount of investment that we would need to be able to adapt. So why can't we get the kind of accuracies that we need in the measurements to predict the level of climate change more accurately? Well, the answer is that we're trying to detect very small trends against a very large background of natural variability. Something like 0.2 of a degree of temperature rise, for example, against a natural variability that sees the temperature vary 10, 15, 20 degrees even on any given day, let alone around the globe. So the measurements have to be very accurate, and the problem is calibration. I work for the National Physical Laboratory in the UK with a National Measurement Institute, and we were set up in 1900 to provide traceable measurements to science and industry. Our lab, and many like it around the world, will calibrate satellite images using instruments like this cryogenic solar absolute radiometer. It measures optical power or light at very high accuracies. And the way that it works is it's a very cold black cavity on the inside that heats up when you shine light on it. When the light is off, you can then obtain that same temperature rise using electrical power, and then you can deduce the optical power from the electrical power. So we can calibrate the instruments very accurately in the lab using this kind of kit, but then the rigours of the launch and the harsh space environment mean that calibration is lost in orbit. Instruments will drift. This chart shows the drift in an instrument called VERS, launched by NASA, and the lines are different spectral bands. You'll see over a period of 10 months, some of the spectral bands are out now by 15 or 30%, and that's over 10 months. Obviously, we can calibrate the instruments once the satellite is in orbit, and there's two main ways of doing that, but both have their limitations. The first way is by very accurately mapping a piece of ground, in this case the Antarctic snowfield, whilst some locals are investigating. And once we very accurately map the reflectance of this piece of ground, you can compare that to what the satellite sees when it views the same piece of ground and see if the satellite's getting it right. The limitations of this are both our ability to very accurately characterise the site, but also the fact that the satellite is seeing that through the atmosphere, so we have to correct for that. The second way of calibrating satellites in orbit is on-orbit calibration. And it works by having a source of light mounted on the satellite, like a lamp, or actually in some cases the sun is used, shining it onto a diffuser into the imager, and when you know the brightness of the lamp or the sun, you can compare that to what the imager is seeing. The limitations of this are that this calibration system, the lamp plus diffuser, or even the sun plus diffuser, can degrade itself in orbit. So although we know how much the imager degraded by, we don't know how much the calibration system degraded by, and we can't correct for that. So the upshot of all of this is that currently our best systems are able to collect data about the climate are only within 2 to 3% uncertainty. And what that means is it's going to take us between 30 to 50 years, potentially even longer for some parameters, to detect the trends in the climate, to know which climate models are getting it right and which to base our investment decisions on. I mean, if you can imagine you're responsible for building the next Thames barrier, and I say, oh, absolutely, I can tell you when you need to build it and how high it needs to be. Just give me 30 to 50 years, and I'll be right back to you. Fortunately, we have Nigel Fox. Nigel Fox runs our Earth Observation Lab at MPL, and he thinks about this kind of problem all of the time. Nigel was thinking, how do we correct for this? How can we get more accurate calibration in orbit? Wouldn't it be great if I could launch myself onto a satellite with the SAR that we use in the lab and calibrate it once it's up there? Now, the kind of satellites that we're dealing with don't take that kind of payload. Sorry, Nigel. But he came up with a way of miniaturising it and mounting it onto a satellite so that it could calibrate satellites whilst they're in orbit. Like existing systems, it uses the lamp plus diffuser, but unlike existing systems, it doesn't stop there. It can detect how much that calibration system has degraded, so we can account for that and correct for that as well. It works by shining a laser into this black cavity and then onto the diffuser, so we know by how much that system degraded. Now you might be sitting there thinking, great, so we get that you've taken this calibration chain one step further back, but how do we know how much the SAR degraded by? Isn't that going to hamper us? And the answer is no. The SAR is coated on the inside with the blackest material on Earth. It lets out less than 0.002% of the light that enters it, which is a UK first. It's carbon nanotubes. This cavity could degrade by a factor of 100 and still give us the accuracies that we need for climate. So across all of that, we can now, if we can launch this satellite, detect climate data at the kind of accuracies that are 10 times better than we can at the minute. 0.3% uncertainty rather than the 2 to 3% that we can currently get, which means that we can bring forward the time that we know which climate models to depend on by a factor of 2 or 3 times. A US economist working with NASA has calculated that that would save about $5 trillion, in fact between $5 and $30 trillion, which is a large range, but both very big numbers, as a result of the better and more timely investment decisions that you would make about adapting to climate change. Now there's a second thing that's important about TRUTH, which is because it has a true polar orbit, it could calibrate other satellites in orbit by passing over the same piece of ground, taking a picture of the same piece of ground at about the same time, and then you can use the image from one to calibrate the other. So you don't just get one super accurate satellite, you get to upgrade the whole Earth observing system. Imagine the kind of difference that that could make to existing satellite services like precision farming or mapping forest cover, pollution monitoring. So I wanted to finish by letting you know where we're up to with this project. We've been funded, along with our partners, by the UK Space Agency to develop the mission concept, and most recently to develop a detailed technical specification and costing. The next stage is prototyping for space, which will cost just over £1 million, and we're already progressing quite well to obtaining that funding. After that, the full cost of launch is between £80 to £100 million. £80 to £100 million to save at least $5 trillion, which is a good business case in anybody's currency. But this isn't just good value for money, this is great science.
Thank you, Jane. And similar, what are the big challenges that you're sort of currently facing, and where sort of could we pick these fantastic brains and get some ideas?
Cheers. So, well, I think we obviously want to launch it, and to launch it we need all of the components, so we do need the full 100 million, even though the novel component of it would probably cost somewhere between 20 and 25 million. So I think there's three main ways that it might be launched. The first is full funding from one government, for example the UK government, and what they have asked us to do is come up with specific UK businesses or academics and how they would use this data that's 10 times more accurate, what the value of that would be to them. So if you run a business that uses satellite data, or if you run a business that has infrastructure and could benefit from this knowledge about when you need to upgrade it and how, we'd like to know that. I suppose the second way of getting it funded is in collaboration with another country, so if you have any links to satellite companies or space agencies in other countries, that would be useful. And then finally, we've just seen about the crowdfunding of the lunar landing. Is this the kind of thing that could get crowdfunded? How would that work? Does anyone have a spare satellite we can borrow? Yeah, any ideas? Welcome.
Brilliant, thank you.
Thank you so much, Jane.